Hello, this is Josiah Winslow recording for his Programming in Java course at MATC for instructor Mark Cribb. Now this is my assignment 2, where I have been asked to implement 6 different programming challenges from chapter 2 of this textbook as a sort of introduction to how Java works, I guess. Luckily for me, I have some experience with Java, and so I've done something which I hope is a little unique. Instead of making 6 different programs, one for each of the challenges, I made a whole program as a testing suite, I guess, for each of them, where you can input a number corresponding to each challenge, and then it will execute that challenge. Now here's a sort of high-level explanation as to how it all works. Here I have an integer list of challenge indices as given in the book. There's 5, 7, 9, 12, 20, and 21. And there are 21 different challenges in the book, by the way. I decided to do it this way instead of 1, 2, 3, 4, 5, 6 because I thought it'd be cool, I guess. And I have a parallel list of challenges right here, which challenge is a custom class that I've made. It's just an abstract challenge with one abstract method called execute, and execute will be defined by each of these extending classes, challenge 5, challenge 7, 9, 12, and it will execute that challenge, and that's how I'm going to implement it. And by the way, this is an integer list instead of an int array because of this one membership checking method that I use later. It doesn't work with int arrays, and it doesn't work with int lists either. It's got to be an integer list. So here I output which challenges they correspond to. Choice 5 is sales prediction, 7 is sales tax, 9 is miles per gallon, 12 is string manipulator, 20 is planting grapevines, and 21 is compound interest. So I have this function called input choice int that basically asks the user which of those choices they want. I put it in a special function, by the way, because it's a little bit more complicated than, hey, what's the thing? And then I get the index of that in the chal indices list, right there, so that I can use that as an index into chal classes to get the corresponding class, and then execute the execute function. And that's basically how it works. But now here are some more details. So the input choice int function that I made takes a integer list called choices, which are the valid choices that you can select. So I have a scanner called in, I always call it in, and an int choice, which will hold the result. So it goes into this do while true loop, which enters unconditionally and loops forever. And then I ask to enter a choice, and then this whole thing, by the way, is wrapped in a try catch because there is an exception that can happen with this if it's not an integer. But it asks for an integer, puts that in choice, and this is why I use a list of integers instead of an array of ints, because a list of integers can use this contains method to check whether or not it contains a certain value. So if choices.contains choice, so if the choice we've selected is in that list of valid choices, it returns the choice. Yay! But if it doesn't, we cry. And we print, that's an invalid choice. You gotta try again. And then it'll loop back from the top, asking for more choices until you get a good one. Now, if this is not an int, then we have an input mismatch exception. And how I have chosen to handle that is, first we got to advance the scanner to the next token so that it doesn't get stuck. I learned that it got stuck the hard way. And then we cry again, but in French. This isn't French, but you know what I mean. No, you don't. And it outputs not a number because you did not input a number. And it will still loop back again forever until it breaks out with the return with a valid choice. And there's only a possibility for an infinite loop here if the user is not very good at choosing. And so that's fed back into here. We get the class, we execute it, and that's fine and dandy. So that's how that works. Now let's get into how each of the challenges works. Now, number 5, sales prediction. It's basically asking us to multiply 62% by $4.6 million. So I have these as final doubles. Doubles because they have decimal points and I want more precision than a float. And final because they are constants. And also I'm not sure if I should have made them private or if just not specifying whether or not they're private or public makes better sense. But these should be only accessible to the class itself. I shouldn't be able to take challenge 5.total sales over here, for example. And the execute basically executes this statement, system.out.format, and I use format because I want to use this special string formatting thing instead of converting to string and doing pluses. I just find that inconvenient. The East Coast division will generate the dollar amount, and then this %.2f means format this floating point number in such a way that after the decimal point there are 2 places, and that's going to look like a money amount in sales %n, which is a new line. And I have to add that because it doesn't do that itself. There's like a print and a print line, and there's a format, but there's no format line. I kind of wish there was, but then again, I understand why not. I mean, you can just add this. So it formats that with the number total sales times total sales %, which if we execute that, and let's choose choice 5, the East Coast division will generate $2,852,000 in sales. And I double checked that with the calculator. That is correct. And actually, for a sec, let's try to run the choice chooser with invalid inputs for a sec to see how they respond. So number 1 isn't a choice, and so it says invalid choice. Number 0 is not a choice either, or -24, or 22, or 8. Those aren't valid choices. And 5.6, well, that's not an integer, is what I mean by not a number. But yeah, that's not a valid integer choice, and neither is whatever that was. And so let's execute choice 5 again so that it ends. This is all good. Now challenge number 7 has to do with sales tax. What we are being asked is to enter the amount of some purchase and then output that purchase amount plus the state sales tax, which is the purchase amount times 4%, the county sales tax amount, which is that amount times 2%, and the sales total, which is the purchase amount plus both the sales tax amounts. And of course, these are final doubles up here for the same reason as last time. So let's test this out. We should expect $1.06 for a $1 purchase because it's $1 plus 4 cents on the dollar plus 2 cents on the dollar. And yeah, that's 106. And if we tried something like $123.45, then it'll output 130.86, which checks out. So now challenge 9, besides the scanner, I've also inputted a few other things for a reason I'll explain a little later. So this is asking us to make a program where we ask the user how many miles they've driven and how many gallons of gas they used, and then divide them to get the miles per gallon. Now, I would have outputted that with format again, normally, with a %f, which is usually what you would do to format a floating point number, but I kind of don't like that format, so I imported the decimal format class, and I make a new decimal format that looks good, and I also use the English locale because otherwise it is not the English locale, I suppose. I like 0 point whatever instead of 0 comma whatever, and some locales have 0 comma whatever as their decimal format thing. And I also have set maximum fraction digits to 340 for this decimal format because this, according to the docs, is the maximum value. And yeah, it looks nice now. Gas mileage, this string, which is the formatting of the miles per gallon value, MPG, new line. And so let's run this. Let's say we've driven 1,000 miles on, let's say, 10 gallons of gas. It's 100 miles a gallon, which is a really good gas mileage for a car, by the way. And let's try again with a different one. So let's say we've driven 100 miles on 7 gallons of gas. Gas mileage is much worse than before, but at least we get some kind of good looking value out of it. 14.28571482. And this is as much precision as the double will give me, miles per gallon. Now perhaps I could have gone with a float for this to get a little less precision than that, but it works. So with that, we go to challenge 12, string manipulator. It asks us to make a program where it asks the user to enter the name of their favorite city, and then I do that with the scanner.next line, and then it will output the length of the string, the number of characters in it, the city but in uppercase, the city but in lowercase, and the first character of the city name, which is 0 because the first index is at 0. All of these are native string functions, so they are easy to get. So let's say my favorite city is the city where I'm currently at now, Franklin. And yep, that's 8 characters. All uppercase looks like all uppercase, all lowercase, and the first character is an F, a capital one, because I inputted it as a capital. And so let's do that again, but this time with a city I used to be at, West Dallas, and let's do the first one in lowercase this time just to see how that works. And yep, that's 10 characters, including the space right there. All uppercase looks like that, all lowercase looks like that, and the first character is a lowercase w. That checks out. And that was a fun exercise. Now here we're at planting grapevines. So a vineyard owner is planting several new rows of grapevines, and she has miraculously discovered this formula for how many grapevines she'll need to plant in a certain row. And then it asks for all the variables and will output a certain value. Now I have a final double tolerance right here equal to 0.15 grapevines. I will explain that later. So here we have enter length of the row in feet, enter the space used by the end post assemblies in feet, enter the space between grapevines in feet, and the calculation of the number of grapevines from these is straightforward. Also, operator precedence for the win, because I don't have to put parentheses around this, which is amazing. Multiplication is a higher precedence than subtraction. Now, this is this is where it gets a little tricky, because while if you have like a fractional number of grapevines, you could just output that as a double. Grapevines are natural numbers. The number of grapevines are going to be something like 0, 1, 2, 3, 4, or 5. It's going to be hard to plant half a grapevine or like a fractional number of grapevines. And even if, you planted one and you cut it off, that's still like a grapevine, right? It's just like a shorter one. But in order to have that outputted in an integer sort of way, I have to do something else kind of complicated. It's not complex, but it is complicated. I don't know what the distinction is. I don't know why I said that. But I calculate the rounded number of grapevines, which is math.rint for rounded integer of the result. Now, despite the name, this actually returns a double, but I guess that's just what they decide to call this. And it's basically what the double would look like if the integer part were cut off, and also if it's 1/2 or greater, then it's rounded to the next number up. I don't know exactly what the behavior is for negative numbers, but that's the behavior for positive numbers, and we are dealing with all positive numbers here because these are lengths. And here I have a string called correctness. I didn't know exactly what else to call it, but this will hold like the output is in the form you will be able to fit blank grapevines, like exactly 2 grapevines, or just about 7 grapevines, or just under 3 grapevines, something like that. Excuse me. So if the number of grapevines is exactly equal to the rounded grapevines, then the number of grapevines is an integer, and we are looking at exactly that number of grapevines, or at least exactly within the tolerance that Java allows for exactness with doubles, because I know that being a binary format, the double format is a problem for some numbers. 0.01 plus 0.02 is not equal to 0.03, stuff like that. Otherwise, if the number of grapevines is more than the rounded grapevines, then it's going to be slightly more than an integer, and we have to say it's either just over or just about, depending on this tolerance value. And that's why we had that up earlier. Let's highlight that. So that's 0.15 of a grapevine. So if the difference between the calculated number and the rounded number is less than 0.15, then it's only slightly more than the number of rounded grapevines, so I say it's just about. Otherwise, if it's more than that, then I say it's just over. And otherwise, if the calculated number of grapevines is slightly less, or if it's less than the number of rounded grapevines, then they're a little less than an integer. And we have to check if the difference between the number of grapevines and rounded grapevines is less than the tolerance. It's almost that number. Otherwise, it's just under that number. And so yeah, this looks nice, don't you think? It's gonna. And here I have to cast rounded grapevines to an int in order to get it to format as an integer with this decimal formatter. So let's see. Enter length of row. Let's say we have a 30-foot row. The end post assembly takes up 3 feet on either side, and the space between the vines is 2 feet. Then I'll be able to fit exactly 12 grapevines. So that checks out, because 30 minus 2 times 3, that's 6, so the result is 24. Divided by 2, 12 grapevines. And that's exact. Now if we did the same numbers, but the space between vines is 3 feet, we get exactly 8. And if we do the same thing, but it's exactly, if it's 5 feet of space between vines, then the result is 4 point something something, and it's just under 5 grapevines. So I'm not gonna be able to plant 5 grapevines quite, but I'll be able to fit like 4 grapevines and almost 5. But not almost, because apparently the value didn't fit within the tolerance. Let's see if I can get some value to fit the tolerance. So let's see, 4.9. Yeah, so if it's 4.9 feet within the vine space between the vines instead of 5 feet, then I'll be able to fit almost 5 grapevines. So that's getting up, inching a little closer. And let's see. Apparently 4.8 would make me be able to fit exactly 5 grapevines. And so let's do one more then with 4.7. I should get a result of almost. Oh, not almost. Yeah, just about 5 grapevines. So that's good. And finally, compound interest. Now this is, I don't want to say tedious, because it's not really tedious, but it's more, I don't want to say pencil pushing either, because I'm not using a pencil. Variable pushing, code pushing, typewriter, I don't know. But this is more mechanical of a process to code than anything. So this is a simple formula for compound interest, where we have to enter the principal amount of money, the annual interest rate as a percentage, and what I have to do is take the input and then divide that by 100 to get the percentage. Or no, from a percentage to get to a rate. Number of times compounded per year, and the number of years. And this is the formula. The principal times 1 plus the interest rate over the compounding frequency to the power of the compounding frequency times number of years. And again, operator precedence for the win. I don't have to put parentheses around this because division takes precedence over addition. And then I output as a money format, just like I did in some previous challenges. Now, it's actually kind of interesting because these kind of questions that Jacob Bernoulli was looking at when he discovered the constant E. Like, it's called Euler's number, but it was actually discovered by Bernoulli. So that's a little bit of a misnomer. Anyways, let's say, and let's look at the question that he was looking at. Let's say I have $1. The annual interest rate is $100, so we're with a really good bank. And we compound once per year. For 1 year, we should get $1 more after 1 year, which is $2. And so, the question he looked at was, what happens when we compound more frequently? So, let's say $1, 100%, and we're compounding quarterly, we get $2.44. Way better than $2. And let's say we are compounding instead monthly, so that's 12 times per year. 261, that's even more than 244, which is also even more than $2. Are we just going to keep increasing our money whenever we compound more frequently and more frequently? Let's see. Let's say we compound weekly, 52 times per year, or just about 52. I think it's 52 and 1 day is 365. 52 and 2 days is 366 for leap years. But, you know, this is good enough. And for 1 year, 269, more than before. And if we keep compounding many times per year, but not too much because apparently Java's math breaks if I input too many 9s over there. I found that out the hard way. I think it has to do with some sort of integer overflow or whatever. Or not integer, some sort of overflow. And it's rounding this value, but the real number is something close to 2.718. It's like 2.71828, 1828, 459045, 235. I don't know the rest. That's what I've memorized, and that is Euler's number, which is the limit as the number of times compounded per year for this equation increases to infinity. And it's really interesting that it goes to some sort of limit. I could talk for hours about like how interesting this number E is. But we are out of time because that is the last challenge that I had to complete in this assignment. So that means my video is done. Alright. Take care. I really hope you liked this assignment, and I hope you like what I did, Mr. Crib. Thank you.